is the Cauchy's theorem. Lagrange's mean value theorem is applicable for only one function. Cauchy's theorem. So let f of x and g of x be two functions which are continuous in the interval closed AB and differentiable in the interval open AB, and their derivatives do not vanish simultaneously. That means there is no common point at which both the derivatives are zero. And the denominator, the function in the denominator does not have equal values at the extreme ends of the interval. That is, g of a is not equal to g of b. Then there exists at least one c belonging to AB such that f of b minus f of a by g of b minus g of a is equal to f dash c by g dash c. Remember, one important point to remember is this c is the common point. It is not that the c is different for, so it is not that we have f of b minus f of a by b minus a is equal to f dash c, and then g of b minus g of a by b minus a is equal to g dash c. This is by Lagrange's mean value theorem. However, the c may be different for both the functions, but Cauchy's theorem says as long as this doesn't happen, there will be one common c where the ratio f of b minus f of a by g of b minus g of a will be f dash c by g dash c. So this is provable by Lagrange's mean value theorem. Of course, we will not get into the proof of it, but this is the Cauchy's theorem. More important theorems for us coming up are the Taylor's theorem. There's again an extension of Lagrange's mean value theorem. So Taylor's theorem with Lagrange's form of remainder. Now, if f of x is continuous and differentiable n plus 1 times on a closed interval a comma a plus h, then for any x belonging to a comma a plus h, f of x is this. So f of x is equal to f of a plus x minus a by 1 factorial into f dash a, x minus a whole square by 2 factorial into f double dash a, so on, and x minus a whole power n by n factorial into nth derivative of a plus this remainder. So let us write this in other form. See, we talked about a plus h. So the common form in which this is written is f of a plus h is equal to f of a, all right, plus h by 1 factorial into f dash a plus h square by 2 factorial into f double dash a, so on, plus h power n by n factorial into nth derivative of f at a plus h power n plus 1 by n plus 1 factorial into n plus first derivative at c, where c is a plus some theta h, where theta lies between 0 and 1. See, this is, we are expanding. A plus h, f of a plus h is f of a plus h by 1 factorial f dash a plus h square by 2 factorial into f double dash a, so on up to here, up to nth term plus this term. This c is a number between a and x here. So what we have done here is a plus h we have taken as x, and c is some number between a and x. So this is called as the Taylor's theorem, and this term at the end is the Lagrange's form of remainder. All right, this is the remainder term, h power n plus 1 by n plus 1 factorial into nth derivative of f at c. This is the Lagrange's form of remainder. So we can remember this Taylor series either in this form, what I just showed here, or you can remember in the form that is here typed, f of x is equal to f of a plus x minus a by 1 factorial into f dash a, x minus a the whole square by 2 factorial into f double dash a, so on, x minus a whole power n by n factorial into nth derivative of a plus x minus a whole power n plus 1 by n plus 1 factorial into n plus first derivative of f at c. Now this is called as Taylor's series expansion with Lagrangian form of remainder expanded about x equal to a. All right, this is the Taylor's theorem about x equal to a. Now you see, we can show that Lagrange's mean value theorem is just a subset of this Taylor's theorem. So if you just take the first two terms, that means these two terms, if we just take, all right, so take in this expression these two terms, what do we get if we are approximating it? So f of x is equal to f of a plus x minus a by 1 factorial into f dash a. So of course this will be, when we limit it to just two terms, then this remainder will be an approximation. So we will get c here, not a, because we are making the approximation leaving out the higher order terms. So f dash c is f of x minus f of a by x minus a. So this is Lagrange's mean value theorem. Okay. So when we stop at this, that means we have ended at the second term. So what we get is this Lagrange's mean value theorem. So Lagrange's mean value theorem is a particular case of Taylor's theorem. All right. Now, next, we can have Taylor's theorem in another form with Cauchy's form of remainder. This is little different. However, most popular is for our purposes, without going too deep into these series. For our purposes, this is, we stick to Lagrange's form of remainder, but we should know the Cauchy's form of remainder. All terms remain same except for the last one. In the last one, instead of having x minus a whole power n plus 1 by n plus 1, we have a different term here. X minus a into x minus c whole power n by n factorial into f of, f of the n plus first derivative of f at c. So that's the only difference. Now, when x, Taylor's theorem expanded about x equal to a, we have seen that. Now the same thing we expand about x equal to 0 becomes Maclaurin's series. This becomes Maclaurin series, and this is a very important series for us. So Maclaurin's theorem with Lagrange's form of remainder. So f is a continuous function and differentiable n plus 1 times. Then we get f of x is equal to f of 0 plus x by 1 factorial into f dash 0 plus x square by 2 factorial into f double dash 0, so on, plus x power n by n factorial into nth derivative of f at 0, plus this last term. We replace, x power n plus 1 by n plus 1 factorial into f nth derivative at c. So not x at c, you just this at c. Now, as I've given in the earlier, when we were doing limits, I showed that we have the standard Maclaurin's series. Yeah. Usually when the remainder term tends to 0 as n tends to infinity, we get what we call as the infinite Maclaurin series. So this is the infinite Maclaurin series. And these are some of the standard series, and some of them we should remember directly, which is e power x, a power x, log of 1 plus x. These are some standard ones that we must remember. Sin x and cos x. Tan x may not be. At least the first two terms we can remember, or if needed, we can derive on spot using this expansion. So this in this application of derivatives, we are showing that a function can be approximated to a polynomial. You have converted any complex function into an algebraic type of function in a series expansion. All right, where these are coefficients, f of 0, f dash 0, f double dash 0, f triple dash 0. These are all constant terms. So we get as a power. Now, to how much power you want to approximate, you can approximate, as I showed you earlier. Just, yeah. So this is the graph of sin x. We know this is the graph of sin x. Now, if I take the first term of the Maclaurin series of sin x, what is that? First term of the Maclaurin series of sin x here, x. Okay. So when I choose that, so I've chosen that, I just get a straight line, y equal to x. So this is the approximation. Now, when I choose two terms, x minus x cubed by 3 factorial. See the next. This is the approximation. Because it is just two terms. It's a cubic function. So it will have a graph like this. So close to 0 and nearby 0, sin x and this curve are matching. And away from, almost like minus pi by 2, less than minus pi by 2 and greater than pi by 2, there is a lot of difference. The two curves diverge. Now I add more terms. So here, the next series that you are seeing here, I have 1, 2, 3, 4, 5, 6 terms. So six term approximation. Now you see here, the curves match more closely. And here I have another two terms, x power 13 by 13 factorial and 15 by 15 factorial. And you see, there is more overlap. So like that, as n tends to infinity, you keep adding the terms in the Maclaurin series. This merges with the sin x curve. So there's a beautiful application of derivatives here, that you can get a function written in a power series form, and then we can use it in different ways. If we are dealing with a region close to 0, then very good. We will be able to approximate it with an algebraic function instead of a transcendental function. These functions, sin x, cos x, tan x, log x, e power x, these are called as transcendental functions, which are non-algebraic. So that is the application. So we can show that the same thing is valid for other graphs also. I'll choose cosine now. So I have shown this earlier. So there's the cosine graph. With the first term approximation, we get this not at all matching. Two terms of the Maclaurin series. This is the graph. Three terms, there's this much overlap. Four terms, not four, 5, 6 terms, a big overlap. And then adding another two terms, see the overlap. So for all functions, we can show it this way. So the third term in the Taylor series expansion of e power x about x equal to a. So let us write the Taylor series expansion. F of x is equal to f of a plus x minus a by 1 factorial into f dash a. This is the second term. The third term is x minus a the whole square by 2 factorial into f double dash a, so on. So this is the third term that is being asked for. So f of x is e power x. So first derivative is e power x itself. The second derivative is also e power x. Therefore, second derivative at a is e power a. Therefore, the third term is x minus a the whole square by 2 factorial into e power a. Very simple question. The Taylor series expansion of sin x about x equal to pi by 6. So how many terms? Let us see. At least 4 terms we can expand. So f of x is f of a at pi by 6 we have to do. Then x minus a by 1 factorial into f dash, sorry, f dash a plus x minus a the whole square by 2 factorial into f double dash a, and so on. So f of x is sine x. What is the derivative of sine x? Cos x. What is the derivative of cos x? Minus sine x. And what is the derivative of minus sine x? It will be minus cos x. Now, so we are expanding about x equal to pi by 6. So what is f of pi by 6? Sine pi by 6. What is sine pi by 6? Half. F dash pi by 6 is cos pi by 6. Cos 30 is root 3 upon 2. Then f double dash pi by 6 is minus sine pi by 6 minus half. So up to 4 terms we can write this minus root 3 by 2. So f of x is sine x. We can write this as f of a, that is half, plus x minus pi by 6, x minus pi by 6 by 1 factorial into f dash root 3 by 2 plus x minus pi by 6 whole square by 2 factorial into this term f double dash, that is minus half, plus x minus pi by 6 the whole cube by 3 factorial into minus 3 by minus under root 3 by 2, and so on. So now we can observe which one is the right answer. So you can see here half plus root 3 by 2 into x minus pi by 6 minus 1 by 4 into x minus pi by 6 whole square minus root 3 upon 12. 3 factorial is 6 multiplied by 2 is 12. So minus root 3 upon 12 x minus pi by 6 whole cube. So this is the correct answer. Now students generally in haste can make this mistake that sine x is x minus x cube by 3 factorial plus x power 5 by 5 factorial minus x power 7 by 7 factorial, and so on. So if I have to expand about x equal to pi by 6, I replace x by x minus pi by 6, x minus a. That's a mistake. That's a mistake because this is the expansion for Maclaurin series about x equal to 0. So these are derivatives, terms are derivatives at x equal to 0. Whereas in this case, the derivatives will be at pi by 6. So therefore, the expression comes out completely different. If we try to do this shortcut, we may think that this is the answer. We may think that this is the answer, but this is actually not the answer. All right. All right. Now just look at this. Now linear approximation means this. F of x is f of 2 plus x minus 2 by 1 factorial into f dash 2. That's it. Third term we will not go for because this is a linear function. Third term will be x minus 2 the whole square. It will be a quadratic function. So now f of x is e power minus x. So what will be f dash x? Minus of e power minus x. E power minus x into minus 1. That's all. So f of 2 is e power minus 2 and f dash 2 is minus of e power minus 2. So therefore the linear approximation is f of x is f of 2, that is e power minus 2, plus x minus 2 into minus e power minus 2. So when we take e power minus 2 common, we get 1 minus of x minus 2. So e power minus 2 into, this is 3 minus x. E power minus 2 into 3 minus x. So A is the correct option.